Okay, so this morning our discussion is going to focus on something called components of vectors. These components are very, very important, and by the time we are done, you should be able to work out, you should be able to find a component of a vector, because you need these components when you're carrying out vector addition and also for other sorts of things for which you need to know how much a vector is in a particular direction. So what we do, the process we carry out when you're trying to find out how much a vector is along a particular direction, that is what is called decomposing a vector or resolving a vector. When you're decomposing a vector or you're resolving a vector, you want to find out how much a vector is along a particular direction. And the directions we are interested in this course are the x and y axes of the xy plane. Okay. So you want to find out how much is a vector along the x-axis and how much is a vector along the y-axis, because normally your vector would not ordinarily point. It will be very rare cases where you have a vector completely pointing along the x-axis or along the y-axis. Most of the time, your vectors which you're going to be working with and the ones I'm going to give you will not point completely along the x-axis or along the y-axis. So it will be necessary for you to find how much a vector is along the x-axis and how much it is along the y-axis. The how much a vector is along the x-axis, that is what you write like this, where a is the vector, then x is the direction in which the vector, we are in the direction in which we are interested in finding the size of the vector. So this should be read as a along x. So how much is a along x? And if you are interested in the y-axis, how much a vector is along the y-axis, you write it like this. So a along y. Are we clear? A component of a vector is how much a vector is along a particular direction which you are interested in. We are only interested in two directions, the x-axis and the y-axis. How much a particular vector a is along the x-axis, that's what we write like this, ax, a being the name of the vector, then x the direction, and along the y-axis we write ay, a being the vector, then y being the direction. Formally, how do we define a component? The component of a vector along any direction is the magnitude of a vector multiplied by the cosine of the angle between its direction and the direction of the vector. Okay. So here, for you to find the component of a vector, you multiply the size of the vector multiplied by the cosine of the angle between the vector and the direction we are interested in. For example, here we have got an example of how to do that. So here we have a vector a. This is vector a in board, and we have got the directions we're interested in. We are interested in the x direction and we are interested in the y direction here. This x direction shown here is the positive x direction, and the opposite of this side is going to be the negative x direction. The y shown here is the positive y direction, and below that you've got the negative y direction. So if you look at this vector a, it has a size. Okay, it has a size, and the arrow points the direction in which the vector is pointing. So we want, what we are interested in when we're working out what is ax, what is the x component of a, what is ay, what is the y component of a. We want to find the direction, what is the size of vector a along this x direction. What is the size of vector a along this y direction? That's what we want to find out. We want to find out how much vector a is along the x direction, how much vector A is along the y direction. So if you take this, the length of the vector A as your hypotenuse, then this end here, if you take it as your adjacent, then this side here, if you take it as your opposite, which is how much the vector is along the y-axis, and this is how much the vector is along the x-axis, you see that you have got yourself a right angled triangle. So you have yourself a right angled triangle. From this right angled triangle, you can get these relationships that AX is going to be A cos theta and AY is going to be A sin theta. So this is your opposites, this is your adjacent, this is hypotenuse, and they are related like this. Is it clear here on how you get your x component and how you get your y component? So always we are going to be multiplying. If we are looking for the x component of a vector, we multiply the size of the vector multiplied by the cosine of this angle. This is the angle between the x-axis and the vector, this theta. So AX, you multiply the size of the vector multiplied by the cosine of the angle. If you are looking for how much the vector is along the y-axis, you multiply the size of the vector multiplied by the sine of the angle the vector makes with the direction you're interested in. This A sine theta is the same as if we get this angle here. If we get this angle here, this angle, if this is theta, then the remaining angle, because we know the x and y axis meet each other at 90 degrees, so the remaining angle this side is 90 minus theta. So if you work out the cosine of that, as per the definition of a component, a cos 90 minus theta, that is going to give you A sin theta. Here we have. So here you have your vector A, then always, so it will be, usually what we do is you create a table like this, where you have the name of the vector in the first column, then what is going to be the x component of the vector, and what will be the y component of the vector. So for vector A, like in our case, the x component of vector A, written AX, that is how much is vector A along the x-axis, that is, as we have seen, A cos theta. Then for vector Y, the AY, which is the y component of vector A, is the size of vector A multiplied by the cosine of the angle between the vector and the direction you're interested in. The vector is this one. For the y part, the vector is this one. The angle between this vector and the y-axis is this angle, That is 90 minus theta. So always you define your component in terms of cosine. So this angle, if this from here to there is theta, the remaining angle from there to there, that's going to be 90 minus theta. Then it turns out that 90 minus theta is actually sin theta. That's why we have A sin theta, and we're going to use this A sin theta going forward. Is that clear? This is how we expect you to find how much a vector is along the x-axis, how much a vector is along the y-axis. Any questions? About how to get the components AX and AY? So AX is A cos theta, AY is A sin theta. Now something interesting happens. When you have a component of a vector, if you know AX and you know AY, you can actually use AX and AY to find the size of a vector, because remember, a vector has got magnitude and direction. So whenever you're talking about the vector, you have to find out what's the size of this vector and in what direction is it pointing. So when you have the components, when you know how much a particular vector is along the x-axis, so when ax is known and when ay is known, you can actually use ax and ay to find out what is the size of a vector. And the size of the vector is denoted like this. So the size of vector A is equal to the square root of ax squared plus ay squared. This is basically a form of Pythagoras theorem, because this being a right angle triangle, we know that A is related to ay and ax as a squared is equals to ax squared plus ay squared. That is Pythagoras theorem. So what you have here is actually that Pythagoras formula here, showing you how to find the size of a vector when you have the components ax and ay. So the size of a vector A is equal to the square root of ax squared plus ay squared. Is that clear? Patrick Malambo, I don't know why you're shifting so much wherever you are. Can you please switch off your microphone? Patrick Malambo, if you're not asking a question, switch off your microphone. Patrick, are you asking a question or not? Because we want that microphone off if you're not asking a question. Are we clear on how we find the size of a vector from its components? So we can find the size like that. The other thing we can also find is the direction in which the vector is pointing, because the direction of a vector, as you can see from here, is given by the angle theta, this angle theta here. That's what gives you the direction. That's how we show direction when it comes to vectors. We use angles. So you will notice that if you have ax, if ax is known and ay is known, these ax and ay are related. The opposite and the adjacent are related to theta through the trigonometric function tangent. So you can proceed to work out this. Tan theta is equals to ay divided by ax. So if ay is known and ax is known, then you work out the tangent of these guys. Then after that, you find the tan inverse, you're going to get theta. Is this clear?
Yes.
Components
Yes.
allow us, components of vectors allow us to break down vectors into, if you have got a vector, then you find its components. Those components tell you how much a vector is along a particular direction, along the x-axis, along the y-axis. But you can also use those components. If you have components of a vector, you can use those components to build a vector, so that you can find what is the size of this vector and in what direction is the vector pointing. That's why we're interested in components. Okay. The other thing is about components. Our components are only pointing in two different directions: the x direction and the y direction. So if you have, remember, these components are still kind of vectors because they have a size, and you can see at the end here there's an arrow there. So a component is actually a special vector which points in a specific direction. Okay? You also look at this one here. The size, the length tells you the size of the vector, then the arrow tells you the direction. So these components are special vectors which are restricted to pointing in specific directions, along the y direction and along the x direction. If you have a bunch of vectors pointing along a specific direction, then those vectors are acting along the same line. And what did we say about vectors acting along the same line? If you still remember what we did here, vectors acting along the same line. The resultant of adding two vectors acting along the same line is the sum of the magnitudes of the two vectors. The direction of the resultant remains the same. So when you get a vector A, you find the x component ax, then you find the y component ay. Okay? Then you get another vector B, you find its x component bx, then its y component by. The ax of this vector of A and bx are pointing in the same direction. So ax and bx can just be added like normal vectors pointing along the same line. The same thing applies to ay and by. Ay and by are pointing in the same line. So you can just add their sizes and the direction of ax and bx remains the same. It will be the x direction. The direction of ay and by will remain the same. That's why components are interesting to us, because with components, after we have found the component for each and every vector, we can simply add the components, the x components, we add them together or we subtract them together. The y components, we add them together, we subtract them together. Then we find the size of the components along the x direction and along the y direction. The direction remains unchanged. So we know the direction, it's the x direction. We know the other direction is the y direction. We just add the x components of the different vectors and we get the size. So once we know what is the sum of these components along the x and along the y, we can rebuild the vectors using this formula. You can rebuild the vectors using that formula because you know how much the x components are along the x direction. You know how much the x components are along the y direction. So you can build vectors from scratch using this formula. You find the size, and also using this formula, you find the direction. Are we clear? So I'm going to show something which I'm just from talking about here before we start looking at an example. So for example, you have this table here. This table shows three vectors. Vector A, yeah. So this table shows three vectors. There are some people who need to be admitted. Okay. So vector A, vector B, and vector C. So vectors A, B, and C. Then with this A, B, and C, we proceed to carry out different mathematical operations. For example, we do A plus B, we do A minus B, we do B minus A, we do A plus B plus C, we do A plus B minus C. These are different mathematical operations you can carry out using vectors, especially A plus B, A minus B, B minus A. We did something similar to that with the triangle of vectors. Where is that? If I can find that quickly. This. We have got vector A, we have got vector B, then we say A plus B. We have got vector A, we have got vector B, then we do B minus A. We have got vector A here, we have got vector B, then we do A minus B. So these operations we are trying to do using components, we have done them before using this triangle of vectors, and we went further to talk about the disadvantages of this method as being tedious, and most likely you will not get the right answer. So with components, things become much easier because the only thing we need to do is for each vector, we need to find out how much it is along the x-axis and how much it is along the y-axis. So for vector A, you need to find out how much is vector A along the x-axis. That is the x component. So this one, AX. For vector A, we're going to give you the size of vector A, and you're going to give you the angle it makes. So that it should be possible for you to work out A cos theta. So you find out what is AX. Then you also find out what is ay, the y component of a. So for each vector a, b, c, you find ax, you find ay. And how do you find the x component for a particular vector? Just to remind ourselves here, ax for a particular vector is equal to the size of the vector multiplied by the cosine of the angle the vector makes with the x-axis. Ay is equal to the size of the vector a multiplied by the sine of the angle that particular vector makes with the x-axis. So that's how we work out these things. So for vector a, you work out ax, what is the x component of a, then you work out ay. For vector b, you work out bx, what is how much is vector b along the x component, along the x-axis, that is bx. Then you also work out this, how much is vector b along the y component. For vector c, you work out cx, how much is vector c along the x component, then also how much is vector c along the y component. Once we know how much each of these vectors a, b, and c is along the x-axis, once you work out these ax, ay, bx, by, cx, cy, then you can work out these operations, a plus b. For you to work out a plus b, you need to find out how much a plus b is along the x-axis. You also need to find out how much a plus b is along the y-axis. Are we clear? For you to work out this, we are adding a plus, yes.
So the screen is, I mean, the board is not showing.
The screen is not showing?
Yes, sir. There's only your pictures is shown there.
Is that what everybody else is experiencing?
No, sir.
I think some people can see my screen.
Yes, you can see.
We can see now.
Yeah, try to either refresh your page or log out, then log in so that we admit you again and see if the result is still the same. Okay. So,
Okay, sir.
for each vector a, b, and c, we now know how much it is along the x-axis, how much it is along the y-axis. These things, a plus b, you're adding vectors. When you add vectors, this is what is called the resultant. This a minus b, you are this a minus b is a form of addition. It's called the resultant. Also, b minus a, you're adding or subtracting vectors, that's the resultant. A plus b plus c, that's a resultant. A plus b minus c, that is a resultant. So when our focus is here, a plus b. For a plus b, you ask yourself, how much is a plus b along the x-axis and how much is a plus b along the y-axis? For you to find out how much a plus b along the x-axis, you just add the x components of these two vectors. The x component of a is ax. The x component of b is bx. So a plus b along the x-axis is actually as simple as ax plus bx. Very simple. Then a plus b along the y-axis. So you have got how much is ax, a along the y-axis is ay, b along the y-axis is by. So a plus b along the y-axis is just ay plus by. Very, very simple. So once you have worked out ax, ay, bx, by, everything else is just straightforward. You're just adding these. So this is going to give you how much a plus b is along the x-axis. Then this is going to give you how much a plus b is along the y-axis. Once you know how much a vector is along the x-axis, how much a vector is along the y-axis, you can use this formula, this one, a version of this formula, to find what is the size of this vector, which has got a plus b, which has got ax plus bx along the x-axis, ay plus by along the y-axis, to find the size of this vector a plus b. You can also use those same things to find the angle which this vector makes. Okay, So that's why we are trying to do this. It makes things very, very simple. So we know how much a plus b is along the x-axis. We know how much a plus b is along the y-axis. Then a minus b. So a minus b, for a minus b, we need to know how much is a minus b along the x-axis and how much is a minus b along the y-axis. So a minus b along the x-axis is simply going to be equals to ax minus bx. Straightforward. Ax minus bx. So you know how much this vector is along the x-axis. Then along the y-axis is going to be ay minus by. Are we clear on what we are doing? We are trying to find out, when you're adding or subtracting these vectors, how much is each of these vectors along the x-axis, how much is each of these vectors along the y-axis. So here, b minus a, so for b minus a, again, we want to find out how much is b minus a along the x-axis and how much is b minus a along the y-axis. So along the x-axis is going to be bx minus ax. So you're using the components. Then here, along the y-axis is going to be by minus ay. There. Then for a plus b plus c, this example is here to show you that you are not restricted to only adding or subtracting two vectors. You can add as many vectors as you want or as are available to you. The only thing is that as you are adding these vectors, the question again is the same. How much is a plus b plus c along the x-axis and how much is a plus b plus c along the y-axis? And how do you work that out? This is how you work it out. You add ax plus bx plus cx. This ax plus bx plus cx is going to give you how much this vector is, a plus b plus c, along the x-axis, and how much is it along the y-axis is going to be ay plus by plus cy. You add the y components. So you're sticking to along this column, along the x component column, the only things you're adding or subtracting are the x components. Along the y component column, the only things you're adding or subtracting are the y components. Then you move on to a, vector a plus b minus c. You can also do something like this, a plus b minus c. That's the result. This is some kind of vector. Okay. Then for this kind of this vector, you also want to find out how much is it along the x-axis and how much is it along the y-axis. And how do you do that? You simply add the components ax plus bx minus cx. Then this gives you how much that a plus b plus c is along the x-axis. Then along the y-axis, you add ay plus by minus cy, and that gives you how much this vector is along the y-axis. Is it clear how we find how much a vector is when you're adding these vectors or when you're doing subtractions, how much a vector is along a particular direction, along the x-axis and along the y-axis? Is it clear to everyone how these quantities are found? If there are questions, please ask now, because this information is what we are going to use next.
Now, sir, can you find the magnitude of these three vectors?
Which vectors? A plus b, a minus b, b minus a. We've got a bunch of vectors there. Which one are you talking about?
Yes, three of them, a plus b plus c. Can you find the magnitude of these three?
Yes, you can find the magnitude of the vectors. The magnitude of the vectors is, you get this a plus b plus c, you square it. This a plus b plus c, you square it, then plus a plus b plus c squared, then the whole thing put under a square root. Like this. You're following this Pythagoras theorem thing here. You follow this. This is AX. So all the X components, the AX plus BX, AX plus BX plus CX squared. You see the squared thing, the square there? Then plus AY plus BY plus CY squared. Then the whole thing under the square root. That gives you the magnitude of A plus B plus C.
Clear.
Is that clear?
Clear.
That's how that thing works. That's why it's a very, once you have this table, finding magnitudes, finding angles becomes a very straightforward problem. Any other question? Okay, so if there are no other questions, we have an example which we can try to start, but we can't finish now. Okay, here. Under section 6, adding addition of vectors along different directions. Addition of vectors acting along different directions using table of components. Consider vectors A, B, and C, which have magnitudes 20 meters, 30 meters, and 10 meters respectively. So vector A has got a size of 20 meters. Vector B has got a size of 30 meters. And vector C has got a size of 10 meters. The vector A makes 45 degrees angle anti-clockwise with a positive x-axis. So the vector A has got an angle of 45 degrees. The vector B makes an angle of 120 degrees anti-clockwise with a positive x-axis. The vector C lies along the negative x-axis. So vector A makes an angle of 45 degrees with a positive x-axis in an anti-clockwise direction. Vector B makes an angle of 120 degrees with the positive x-axis in an anti-clockwise direction, and vector C lies along the negative x-axis. The one thing I want to mention about angles is there is a way in which we measure angles when it comes to vectors in this physics course. The angle theta by convention is measured from the positive x-axis in an anti-clockwise direction. All angles, including this theta angle is the angle which gives you the direction of the vector. So we give direction of a vector, the direction in which the vector is pointing using this angle theta. We measure it from the positive x-axis. We go in an anti-clockwise direction. A clock goes the other direction, clockwise direction, down like that. As we go up and the other way around like that, anti-clockwise direction. Any angle, since we have agreed to say we are going to be measuring angles in an anti-clockwise direction, and if we measure them in an anti-clockwise direction, these angles are positive. Any angle which is going in a clockwise direction, that angle is going to have a negative sign, showing you that the angle is pointing in a clockwise direction. So with this information, vector A, B, and C, with those sizes and the angles, we can plot this A, B, and C on the XY plane, showing clearly what the size is and what the angles are, as shown below here. So this is my attempt to portray the same information. So I have got my XY plane, as you can see in blue. So this side, I have chosen this side to be the positive x-axis, and this positive x-axis is where I start measuring the angles. All my angles will be measured from the positive x-axis, and they will move in an anti-clockwise direction like that. Then the opposite of the positive x-axis is the negative x-axis. Then on top here, I've got the y-axis. The top part is the positive y-axis. The bottom part is the negative y-axis. As you can clearly see, this black line, this black vector, this is my vector A. And on top of this line, I have put the name of the vector as A and the size of the vector, 20 meters. Then also from the positive x-axis, I show with this black angle here that the angle is 45 degrees. So all the information I need to portray a vector is there. This vector has got a size, it has got a name, it's vector A. The size of this vector A is 20 meters, and also the angle in which it's pointing here, 45 degrees, and it's pointing in that direction. This angle, this arrow shows that this line is a vector. The arrow shows that the line is a vector, and the angle 45 degrees shows you the direction in which the vector is pointing. So that is enough information for us to say A is a vector of size 20 meters at an angle of 45 degrees from the positive x-axis measured in an anticlockwise direction. Then we have vector B, the green one here. Vector B, as you can see, it's a line, the green line. It has got an arrow, so that shows you that that's a vector. Then what's the name of the vector? Vector B, and the size is 30 meters. And the angle it makes is 120 from the positive x-axis. As long as you write the name of the vector and how much it is on this line, you don't have to draw them according to scale, because clearly, as you can see, I think physically the length of my 20 meters and these 30 meters are almost the same. But the fact that I've actually stated, say, B is 30 meters, that takes care of, we don't have to draw everything according to scale, but it should be something which people should be able to see. Then I move on to vector C. Here is my vector C. It's got a size of 10 meters, and it lies along the negative x-axis, like you have been told. If a vector lies along the negative x-axis, if you measure its angle from the positive x-axis, as you can see this red arc here, you get an angle of 180 degrees. Is this clear? Yes. The information about our vector we have presented in form of a picture. We have plotted them on the XY plane. You don't even need, for this thing, you don't even need a graph paper. You just get your plain paper, then you draw XY plane, then whatever, a rough estimate of what 45 degrees are supposed to be, but you tell us this angle is 45 degrees, 120. These angles are not drawn precisely. I don't think that is 45 degrees. I also don't think that is 120 degrees, but I've shown that these angles, this is supposed to be 120 degrees, this is supposed to be 45 degrees. Okay, so with this information, the next task is to find for each of these vectors what are their components, and that is what is worked out here. So we started late. Do you guys have a class coming up next?
Yes, chemistry is coming up at 9 hours.
Okay, fine. So we have to end here, Anga. So we are going to continue on Monday. Okay, since you guys have a class coming up, so we're going to continue on Monday. All right. No questions, hopefully, because we don't have time for questions. All right. So I'll stop sharing. So see you on Monday, where we're going to look at this table. The video will be uploaded to YouTube as usual.